Okay, welcome back everyone. In this video, we're going to take a look at RC circuits, and this video is going to focus more on kind of the quantitative aspects of the circuits, and the next video I'll go into a little bit more of the theory. So this is number 88 from chapter 26, and we're trying to do a couple of different things with RC circuits. First of all, we're integrating the battery power to find the total energy supplied by the battery. We're integrating the power in the resistor, I squared R, to find the energy dissipated in the resistor. And then we're finding the final energy stored in the capacitor and showing that this is the difference between our answers to parts A and B. And finally, we're going to find the fraction of the energy from the battery that gets stored in the capacitor and look at how it depends on the resistance R. Okay, so let's start off by recognizing that the current as a function of time, I of t, is dq dt, because that's the definition of current. In this case, it's E over R times e to the negative t over RC. And you can find this in the reading in the chapter, so I'm not going to derive this right now. I'll actually show you that in the next video. So let's just accept that this is kind of how it works. So we want to integrate the battery power because we know that basically dE is going to be equal to E. Sorry, let me try that again. So the power in the battery is equal to voltage times current. Okay, and we are given that the current is a function of time, and the energy is actually going to be power times time. And so if we want the energy, we have to take basically a small amount of power dissipated at a particular current, and we have to integrate over all time. Okay, so essentially what we're doing is we're integrating from 0 to infinity ei of t dt. Okay, and so that's where that t comes in. Alright, so we essentially want to write it kind of like this, that we want the integral from 0 to infinity, and that e can come out, and I of t is going to be e over r, e to the negative t over rc dt. Alright, well let's take that out of there, and let's just write this as e squared over r, and we'll evaluate that. Okay, so this is the energy stored in the battery. Okay, well, we're going to have e squared over r. And the neat thing about doing an integral of the exponential function is we just need to plop down a constant, and then we have e to the negative t over rc evaluated from 0 to infinity, and that's going to give us e squared times c with the negative sign. R's cancel out, and when I evaluate this when t is equal to infinity, that's going to give me basically e to the infinity power, or 0, and then e to the 0 power is going to give me 1. So another way of saying this is that the total energy stored in the battery is going to be C E squared. Okay, so the capacitance times the voltage squared. Okay, so far so good. In part B, so there's our answer to part A. In part B, we're going to do the same thing, but we're going to do this with the power in the resistor. And so now I'm going to have dE is equal to I squared R dt. Okay, because there's my power. All right, and so we're going to square the entire expression for current. So we're going to have basically uh, e squared over r squared e to the negative 2t over rc, and we're going to have to integrate this from 0 to infinity with respect to time. Okay, again, my e squared over r squared can come out. And the other thing that I can pull out of this is just like up here where I pulled out negative RC, same thing, but this time it's going to be negative RC over 2. Okay. And, oh, let's not be silly. I forgot to multiply by an R because of this R right here. So there's actually another R right there. And so my R squared cancels out. And I'm still going to have to evaluate my integral from infinity to 0 of e to the negative 2t over rc. Okay, and this is going to turn into, this is in the resistor, by the way. Okay, sorry, I'm having brain farts all over the place. So the energy in the resistor is going to be basically C e squared over 2 with the negative sign times 0 minus 1, and so that's going to be 1/2 C e squared. Okay, so far so good, right? I think the math checks out. And this is going to be the energy dissipated in the resistor. Now in part C, we know that the energy stored in a capacitor is equal to 1/2 QV. And that's an equation that I plucked from way back in chapter 24. But we also know that Q is actually a function of time. It's the charge, and this is as basically as time goes to infinity. And so what we can do is actually write an expression for Q of t. It's capacitance times voltage times 1 minus e to the negative t over rc. And this is another equation that I kind of just plucked out of the book, and you can find that a little bit later on. And we want the limit of this expression as t goes to infinity, and that's just going to be equal to CE. You can check my math, but it's basically 1 minus 0. So this gets plugged in for the charge here, and so the energy in a capacitor is 1/2 times CE, and then the voltage itself is just E. And this gives us that the energy in the capacitor is 1/2 CE squared. Okay, now as a check for this, if I take the energy of the battery and subtract the energy of the resistor, I'm going to have CE squared minus 1/2 CE squared, which amazingly enough is 1/2 CE squared. So I know that I've done that correctly. Okay, and finally in part D, we want to find kind of the ratio of the energy in the capacitor to the energy put out by the battery. So that's simply going to be 1/2 CE squared over CE squared, which is just a ratio of 1/2. And what this tells you is that in an RC circuit, after a long period of time, half of the energy gets stored in the capacitor. The other half is dissipated. And you might ask, well, where's the dependence on R? There isn't a dependence on R. All that R does is it adjusts the time factor, RC, so that you might have to wait a little bit longer for the energy to go to the capacitor. But in the end, you're going to always have the same percentage. So that's it for this one. Thanks for tuning in, and we'll see you in the next video where we compare RC circuits to air resistance. See you next time.